Slido, any chance we can go over how to format arrays into our tables? Example showing an array of tasks that relate to a project. What do we think? What's the best way to store arrays in our database? We went over this last week. What's the best way to store an array of data in a database? Another table. Boom, you got it, Dennis. We don't store arrays in columns, remember? We don't store an array type as a data type. We would want to create a new table, and for each item in the array, we create a new row, and then we link back to the original table with a foreign key. Okay, remember to normalize your data schemas. That's part of the normalization process. How to nest it in the API response. Okay, if you were nesting it in the API response, then you would just need to do a join on that separate table, and then you just have to parse your data. I think we're going to do that at some point, if that was the question. Okay. Let's get started. How was the sprint challenge, by the way? Everybody feel okay about it? I realized there was a lot of material to cover in a limited amount of time. But other than that, how did it go? Yeah, it was a lot for 3 hours. It was. By the way, if you're wondering how to reverse Don's link, this is how you would do it, if you're curious. Yeah. All right. So authentication. This is our last web sprint. Come a long ways. So there's some really good stuff coming up over the next 2 weeks. So get ready. So authentication. Authentication is actually it's a really complex and an important topic in development. It's something that's constantly changing as technology gets better. You know, as computers get faster and processors get faster, security has to change to keep up with it. Some people actually spend their entire careers working on authentication, okay, and cryptography and all of these security topics. Other security related fields. It's really, really interesting stuff, but it's also really complex when you get into the weeds. We've spent all this time learning how to set up endpoints, right? How to store data, but that really goes so far unless we learn how to protect our data. So we don't need to go into the weeds as like a security engineer would, but we still need to know the basics of how this stuff is done. Okay, if we don't know the basics, hackers are going to be able to get into our database and essentially steal our data. Okay, we don't want that to happen. We want to take all the measures that we could possibly take to prevent something like that from happening. You'd actually be surprised at how many large companies have terrible security when it comes to their sites and their apps. Even today, like you see examples of it all the time, right? The Equifax hack, right? Which leaked credit card info and driver's license info, social security numbers, and addresses for millions of people, right? Not good. All because they had some bad security in their back end, okay? So we can't protect our sites from hackers 100% of the time, but we can take measures to prevent the most common attacks and to try and contribute to an overall secure internet, right? Our users are trusting us with their data, so let's not let them down. Yeah, I always feel so bad for the engineers that are working at companies when they get hacked or they leak data somehow. It's probably not the engineer's fault that's working there currently, but they take the blame for it. So anytime you see something in the news, it's like, oh, some company got hacked and lost a bunch of data, or their website's down, or something crashed. Feel a little empathy for those developers, because that's going to be it's going to be you someday sitting in that chair. So let's talk about authentication. First of all, do you think when I say the word authentication and the word authorization, do you think authentication and authorization mean the same thing? What do you think? No, they don't mean the same thing, okay? These two words are often used interchangeably, but they are not the same thing, okay? Authentication, or authn, which is sometimes referred to as, is when our web server verifies the identity of a client, okay? It's like when they log in, or when they create a new account, or try to reset their password, okay? It's essentially asking the question, who are you? Authentication is asking, who are you? Okay. Authentication, or sometimes referred to as authn. Authorization, on the other hand, or authz, is a little bit different. Okay, authz comes after authentication, and it's when our web server already knows who's making the request, but it's determining the type of access, if any, the client should have to a resource. Okay, it's asking the question, what do you want? So authentication is asking, who are you? Authorization is asking, what do you want? Okay, permissions, right? So it's like you're going to a basketball game. Okay, let's say you're going to a professional basketball game. Authentication is when you hand over your ticket, right, to get into the arena. They're authenticating that who you say you are, that you have access to the game. Right? And then since you now have a really cool job as a software engineer, they give you a special VIP pass, okay? Now, once you're in the arena, you can now flash your VIP pass to get into special places, right? To get into the special box seats. It's like authorization. Okay, so authentication is asking, who are you? Authorization is asking, what do you want? We're actually only going to be talking about the first part of this tonight, which is authentication. See, I just use them interchangeably. It's tough. We're going to be talking about authentication tonight, the first part of this. Okay, who are you? So building a proper authentication service is actually really, really hard. There's a lot that goes into it, especially if you have a lot of users. But for the most part, most of the time, it actually just boils down to a few core principles. So a fully fledged authentication service is going to be hard, but for a simple application, it boils down to a few core things. Core principles. The first one is requiring strong passwords. The second one is properly storing passwords. And the third one is preventing brute force attacks. Okay, these are the three core principles of authentication. So let's talk about the first one, requiring strong passwords. This can be kind of annoying, right, for users. We've all tried to sign up for sites that have ridiculous password requirements, right? They say that you have to have exactly 3 numbers and 2 symbols and a space, and it can be has to be between 20 and 30 characters, and it has to have your dog's name in it, and blah, 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 right? Sometimes they just get ridiculous. So we actually don't have to get too crazy with this one, but it's a good idea to enforce some kind of minimum requirements. Okay, maybe require it to be longer than 8 characters and have at least one number and symbol, right? And then call it good from there. That's reasonable, right? So requiring strong passwords by just enforcing some kind of a minimum requirement is always a good idea in your authentication system. So though they do help, password requirements do help, they're not enough security by themselves. Okay, we also have to store the passwords securely in our database, which brings us to the second core principle, properly storing our passwords. Okay, up until now, we've taken all of the info from our request bodies and we just stored it directly in the database without changing anything, right? We just take that info from the user, we store it in the database, call it good. And this works fine for basic info like product names or email addresses, but it doesn't work very well for passwords, okay? Let me ask you this, pose a situation to you. How many of you know someone who uses the same password for everything? If you do that yourself, you better fix it after this lecture and sign up for a password manager. Yeah, everybody knows someone, maybe your husband or your wife or your grandma or your mom or your dad, or even you yourself. Everyone knows someone that uses the same password for everything, right? It's a lot easier to remember when you're logging into stuff. So why is this a terrible, terrible thing to do? Well, let's say that you go sign up for my new cool Trinkets app. Okay, remember the Trinkets app? So let's say when you go create an account through my API, I take your password and I store it in my database as plain text. Okay, I don't try and do any encryption or anything special with it. I just store it directly in the database. Okay, cool. It works. You can now log into my app and use the Trinkets app. Now let's say later down the road, due to my negligence as the developer, our servers get hacked and every one of our email addresses and the associated passwords are leaked to the hackers, okay? So since I was storing your password in plain text and you use the same password for everything, the hackers are now able to take your email and password combination and use it to log into like your bank account using the same info that they stole from my database. Okay, not good. So if you're using the same password for everything and someone out there is storing it as plain text, that password is now compromised everywhere you use it. So if you're using the same password for everything, you're essentially putting your trust in every single developer in the world that works on the applications that you're developing. And that's probably not a great idea, right? So the key takeaway from this lecture, if nothing else, is to never, ever, under any circumstances, store user passwords or any other sensitive info as plain text in your database. Okay, never do that. You'd be surprised at how many big companies have been caught doing this. Like it seems pretty obvious that we shouldn't be doing this, but you'd be surprised at how many big companies have been caught doing this. Companies like T-Mobile, right, and MySpace got caught doing this several years back. A lot of big companies were doing this. Okay, so because MySpace gets hacked, you might lose all your money if you're using the same password for everything. So those of you that are doing that, go get a password manager. PlayStation, right? Yeah, another big one. Facebook. So what are our options? Well, we could encrypt it, right? Meaning we take the plain text and we use a secret key to jumble it all up so it's unreadable without that secret key. But what's the problem with encrypting our passwords? Why isn't that good enough? Because it can still be decrypted, right? It's still a reversible process. So if the hackers got into our database and they got our encrypted passwords, but they also got our encryption key, then they could still reverse all of the encrypted passwords back into plain text, right? And it didn't really do us any good. So encryption is not enough. Okay, we need a non-reversible way to hide our users' passwords in our database. So there's this thing called cryptographic hashing, which does just this, okay? It takes some plain text and it runs it through some crazy mathematical algorithms, and it produces a seemingly random alphanumeric string as a result. So this would look something like it'd be like a function that you would call, right? You'd call like hash and give it some string, and it would output something like this. Okay, so it seems like it's just outputting kind of a random string. This isn't an encrypted string. This is a hash. Okay, but it's not actually random. If we run the same hello world string through the same hashing function that uses the same hashing algorithm, we're going to get the same result every time. Okay, we're going to get the same string every single time. What we can't do is take this hash, take this crazy string. We can't reverse this back into hello world. Okay, it's a one-way process. It's irreversible. That string of that original string of hello world is now gone. We can't get that back. We just have this hash. Okay, so this isn't encryption. It's not encrypting that string. We can't reverse it back to hello world. The hash that gets produced is actually going to be the same length no matter what the length is of the string that we're sending it. Right? If we send hash hello universe, right? That's going to be a different length, a string of a different length, but it's still going to produce a hash of the same length as hello world. I don't actually know what the hash of that one is, so I won't even try. So you can kind of think of it as like a fingerprint for a small piece of data, okay? It's unique to that hello world string, and the hash, the same hash can't be generated with a different string. Okay, it's unique to that one string. It's like a fingerprint, and it's irreversible. So there's actually a bunch of different hashing algorithms that do this sort of thing, that produce different sized strings and different results. One is MD5. That's actually the one that I use right here to encrypt hello, or to hash hello world. So this is an MD5 hash. There's some other ones called like SHA-1, SHA-256, bcrypt, Argon. There's a bunch of different ones. Some of them are newer and faster than others. This one, MD5, is actually really old. It's been around for quite some time. And they're used for different things. Okay. So now we can store our passwords in our database as hashes instead of plain text. And it gives us some protection, right? Since a hacker can't easily tell that this hash equates to hello world, right? They're not able to get that original password back. And so now when we store our password as the hash in the database, when someone comes to log in, all we have to do is hash the password that they give us when they're logging in, hash it again, and see if it matches the hash that we already have. Okay, so we can still compare hashes. We can still compare that password to what we got when they signed up, but we have no way of knowing what the actual plain text password is, since it's a one-way operation. So with this newfound knowledge of cryptographic hashing, why is it a red flag when websites limit our passwords to a maximum number of characters? Let's say you go sign up for some application and they say, your password is too long. They can only be a maximum of 25 characters. Okay, why is that a red flag? You hit it on the head, Rose. Michelle. Because there's no reason to limit a password. When you hash a string, the resulting hash is always going to be the same length, no matter the length of the string. It doesn't matter if this hello world string, it doesn't matter if that's 100 characters, it doesn't matter if it's 10 characters or 50 characters, it's always going to result in the same length of hash. In this case, 32 for MD5. So if a website is limiting our password to a maximum length, then that means they're probably not hashing it, right? They're probably storing it encrypted or storing it in plain text. So it should always be a red flag when a website limits your password length, because there's really no reason to, because if they're storing it as a hash, it should be the same no matter what. All right, any questions about cryptographic hashing? So we're still left with another potential attack vector, something called brute forcing. Okay, so that brings us to the third core principle, is preventing brute force attacks. So who knows what brute forcing is? It's kind of a crazy sounding thing. Who knows what brute forcing is? Yeah, exactly. It's when attackers, they essentially go to our login page or our database, right? And they essentially attempt to guess a password over and over and over and over again, hoping they'll eventually guess the correct one, right? That's brute forcing. Just guessing over and over and over again, knowing that eventually you're going to guess the right one. Now, they don't do this themselves, okay? These hackers don't just go to your login page and start at 0 and then press enter and then start at 1 and try and guess every single known password. That would be really slow and take forever to find the correct password, right? Instead, they write programs that do it for them at a scale of like millions of passwords per second. Okay. So if you thought you were clever by like replacing the letter O with a 0 in your password, bad news, it can still be brute forced in a relatively small amount of time. Okay, so that's why it's important to have strong passwords. So going back to the example of hackers stealing my trinkets app database, okay? Let's say that I knew a little bit of what I was doing when I built it, and I hashed all of the passwords using this MD5 algorithm. So now we have a bunch of MD5 hashes sitting in our database. Are we safe? Is hashing those passwords with MD5, is that enough? Not quite, right? Not quite yet. Turns out that these hackers, they actually know how to run a hashing function themselves. So what they do is they're going to go create these huge precompiled tables of essentially every possible password hashed with the same algorithm. It's called a rainbow table. Okay, so they're going to go create these huge tables with every single possible password that's already been MD5 hashed. Okay, and when they do that, it's called a rainbow table. So they're essentially going to have a database that's like MD5 hash and then the associated password, right? This is kind of what it would look like to them. So in that case, they still have our database, right? They have our database info that was leaked. They have our MD5 hashes. They're able to say, all right, I want to find the password for Vlad's account, right? And they know that the password for Vlad's account is this MD5 hash, right? This 5EB63BBBE0, whatever. So all they do is they come to their rainbow table and they look up that MD5 hash and they see, oh, there we go. The associated password is hello world. We now know Vlad's password, right? They can just look up that hashed password and they can get the plain text associated with it. So it's still not enough to simply hash the passwords. So this is one type of brute force attack. There's many others. And there's a number of things that we can do to prevent these brute force attacks. One of them being intentionally slowing down our hashing function. Okay, that's kind of crazy. That's kind of crazy sound. We've never tried to intentionally slow down our code, right? How do we intentionally slow down our code? What's something that we could do to make our code slow on purpose? It's kind of backwards, I know, because we're always trying to speed up our code. But in this case, to prevent these brute force attacks, we can try and slow down our code. Put Sarah in charge? No. Just use JavaScript? Yeah, that would make it pretty slow in most cases. Adding some unnecessary loops. So we can actually do it by introducing something called a time complexity. Okay, a time complexity. We can create a time complexity by simply hashing our plaintext string and then creating a hash of the resulting hash and then hashing that result and then hashing it again and hashing it again over and over and over again until it essentially slows down enough to prevent these rainbow tables, okay, to prevent these brute forces. Let's look at an example. So I created this script really quick in JavaScript that will hash something with MD5. This is what it looks like if you're interested. It just takes 2 arguments, a string, and the number of times to hash it, the number of rounds. So if I say node MD5 and we want to hash the string hello. It hashed it 1 time. This is the resulting hash, right? This 5D41. And you can see it took 0.8 milliseconds, really, really quick, right? So let's try and slow it down. Let's increase the rounds by passing another argument. Let's say 10. Let's try and hash it 10 times. So it's going to hash hello, and then it's going to hash that result, and hash that result, and hash that result 10 times. Let's see how long that takes. All right, we have a different hash, right, because it's hashing something different. But that one only took 0.4 milliseconds, still actually faster than the original one. I don't know how that works. It's such a small amount of time that it's so variable in this case, right? It's still doing it very, very quickly. What if we increase it to 100? We do 100 rounds. All right, that's going to bump it up a little bit, 1.8 milliseconds. Let's bump it up to 1,000 rounds. Let's see how long that takes. And it's making it a little bit longer. It's still 5.2 milliseconds. That's still really, really quick. Let's try bumping it up to 10,000 rounds. Okay, 10,000 rounds takes 44 milliseconds. Still pretty quick. Let's bump it up to 100,000 rounds. That one only took 265 milliseconds. Still fairly quick, right? To hash that hash over and over and over again 100,000 times, it only takes 265 milliseconds, but it's still slowing down a little bit. Let's try it 1 million times. Let's see how long that takes. 1 million rounds of hashing. All right, that took 2.6 seconds. So that's pretty slow, relatively speaking, right? This speed is obviously very dependent on the hardware that it's running on, right? It's dependent on your CPU speed, the type of computer you have. But slowing down our password hashing even just a little bit on every single request, like 1 or 2 seconds, it has a big effect on hackers who are trying to generate these rainbow tables, to the point of it not even being worth it for them to generate them. Okay, we're talking like on a scale of days versus years, just by introducing a simple time complexity of a couple seconds. Okay, let's say that a hacker wanted to generate a rainbow table with 100 million different hashes. 100 million different hashes, and let's say that each hash took 2 milliseconds to generate. Okay, if you calculate that out, it's actually going to result in only about 55 hours to generate that rainbow table, which is about 2.5 days, okay? Not that long. But let's say we introduce a time complexity and we make that hash take 2 seconds to generate instead of 2 milliseconds. Two seconds per hash instead of 2 milliseconds. That's going to bring that time complexity up. And when they try and generate their rainbow table, it's going to take 6 years. Okay, no hacker is going to try and spend 6 years trying to crack a single table of passwords. It's just not worth it to them. So you can see a relatively small amount of time for our users, for our requests, results in a large amount of time for them trying to crack it. So yes, this is a case when being slow is an advantage. We kind of want to intentionally slow down our code to prevent these brute force attacks. So using hashing algorithms alongside these time complexities, it results in something called a key derivation function. It's a hard word to say, a key derivation function. Okay, if you remember derivatives from math class, essentially a key derivation function is when we introduce time complexities to these hashing functions. So it's essentially saying, take a hash, introduce a time complexity, and it's going to equal some kind of a new hash, right? And we just do that over and over again until it slows down enough. A key derivation function. It's basically just a function that gives us a hash derived from another hash. So we can try to write this key derivation function ourselves, but we might get things wrong, right? We could potentially put our passwords at risk if we don't slow it down enough. We might use a hash that's not totally secure. We could mess things up if we try and do this ourselves. We should really never try to invent our own hashing or our own encryption functions, unless we're like cryptographers or mathematicians, right? We should use stuff that's already out there that's proven to work. So let's use an existing password hashing function called bcrypt. It does just this. Bcrypt is a key derivation library that takes care of a lot of stuff under the hood for us. Any questions about anything we've just covered? Pretty cool stuff, right? Sometimes we have to kind of get into the minds of hackers to understand how they're trying to compromise our security and how we can circumvent them. And it's stuff like this, right? Introducing time complexities and not storing stuff in plain text, hashing passwords instead of encrypting them, right? It's all stuff that makes our applications a little bit more secure, stuff that's not obvious when you're just coding an application from scratch. Nothing that a library is going to force you into. These aren't patterns you'll be forced into. It's just the knowledge of them that will help you become a better developer. So Stephen asked, does slowing something down using a hashing algorithm, does it affect the average user of the software? Yes, a little bit, but not enough to make it really worth not doing, right? In this case, we are slowed down when we hash our algorithm, or when we hash our string 1,000,000 times. Okay, essentially that means when they sign up for an account and we're hashing their password, it's going to hash it 1,000,000 times, and it's going to take about 2.5 seconds. So their request, when they actually make that API request, it's going to be 2.5 seconds longer than it would normally be. But in the overall scheme of things, that's not really that noticeable, because you're still already making a request across the internet, which might take a second or two. So slowing it down, yeah, it's going to slow down the user, but it's not really going to be that noticeable. And the benefits that we get from doing something like that far outweigh the time that it takes to do it. Good question, Stephen. So Aislinn, you asked, are there other ways to encrypt a password other than bcrypt? So remember, we're not encrypting a password, we're hashing a password. So bcrypt is a hashing library. It's a key derivation library that helps us hash passwords. There are other libraries and other algorithms that help us. There's one called Argon 2. There's one called scrypt. There's a lot of different ones that we can use, but they're all hashing functions, right? They're not encryption. They're one-way hashing, cryptographic hashes. All right, any other questions? We actually have a lot of time tonight, so feel free to ask any questions you have. All right, let's take a 5-minute break, let all of this soak in, and I'll see you in 5. Okay. Yeah, there's actually some really interesting discussion going on in Slack. Yeah, I mean, introducing these time complexities, it's not a solution that's going to work indefinitely, right? Because every single day, every year, computers are getting more powerful exponentially, right? So maybe that hashing that MD5 string a million times only takes 2.5 seconds right now. But maybe next year it'll take 1 second. Maybe the year after that it'll take 5 milliseconds, right? So as computers get faster, as processors get faster, we have to continue to increase our time complexities to solve for that, right? That's like something that the blockchain does. That's what Bitcoin does, is they exponentially increase their time complexities to offset for the faster processors. And yeah, if something like quantum computing or some kind of supercomputer, some kind of biological computing or something came out and actually worked, then it would probably break most of the internet. It would probably break most of the internet's encryption, most of the internet's hashing, and it would probably be chaos. Right? It might cause our society to collapse. Who knows? But that's a real concern, right? If something is able to break all of this encryption on the internet, then pretty much everyone's screwed. Unless the security methods and the authentication methods and the hashing algorithms, unless they evolve too, right? Maybe we have these quantum computers that can break all of the encryption on the internet, but we also now have quantum hashing algorithms that work with it. So anyways, fun side discussion there. I could talk about that for quite some time. So Ruth, you asked, is it helpful to limit login attempts to prevent brute force attacks? Yes. So introducing these time complexities, that's just one way of preventing these brute force attacks. Okay, so there's other things that you can do as well, like limiting login attempts, right? Maybe if someone tries to log in, has an unsuccessful login attempt, maybe like 3 or 4 times on the same account, you can tell that something might be a little bit fishy and you can lock their account, right? Or maybe you rate limit people that visit your API. So you only allow a certain IP address, like 100 requests per minute or something. Then if they try and request something that's over that, some more than 100 requests per minute, then you'll give them an error and say you can't do that. You're trying to request too much time. So there's other things that you can do to kind of prevent these brute force attacks. All of them working together usually do a pretty good job, but you still can't prevent 100% of hackers, right? I don't know if we're ever going to have a chance to implement something like rate limiting or limiting login attempts. We'll see if we have some time to cover that at some point. Yeah, I mean, iOS implements that, right? If you try and unsuccessfully log into your phone more than like 10 times, it'll lock it. Or if you have it set up, it might erase all your data, which is not good if you forget your password, but could be good if your phone falls into the wrong hands. So let's talk about bcrypt. So bcrypt is a key derivation function or a key derivation library that helps us with hashing our passwords. The JavaScript implementation of it is called bcrypt.js. Here's the link. So bcrypt, it gives us a few things out of the box. Okay, essentially it gives us password hashing and verification functions. Okay, it has automatic time complexities. It automatically builds that in to the hashing function. It has automatic password salting, which is another method of preventing these rainbow tables. Okay, does anybody know what password salting is, or what salting is just in general? What is salting? Adding a little flavor. Yeah, it's just adding some random characters, right? Random junk data added. So it's essentially taking your password. So it's saying, let's make an MD5 hash of your password of hello world. But instead of just hashing our password, we're going to append some random string to it. We're going to say like some random salt 1, 2, 3, 4, 5, right? Just something like that. And when you do that, you're going to produce a different hash than would result from just the regular plain old hello world table, or the hello world string. That's going to equal something like this, which is different than what we had in the rainbow table. So if you take some kind of data that can be reproduced, right? It can't just be some random string because you have to be able to reproduce it. But something that's unique to that user or that piece of data, and you append it to the original password or the original string, which is called salting. Okay, that's called the salt. And then you hash those two both together. It's going to result in a hash that can't be reproduced in a rainbow table. Okay, so bcrypt, it gives us salting by default. Out of the box, it gives us time complexities, and it gives us functions that we can call to actually create our hashes and to verify our hashes, which is really, really nice. So let's get our project cloned down. Make sure you get it cloned down, npm installed. Yeah, Bradley, that's a good idea. Salting with your security question answers. Okay, so get the project cloned down. Make sure you run npm install. Let me make sure I pushed up all my changes this time. Yeah, we're good. Okay, and then open it up in your code editor. And let's just look through this code real quick. This is just a simple application that has some routes. It has an auth router and a user router. If you look at each one of those, the auth router, it just has endpoints for registering a new account and logging into an account, an existing account. And then the user router, which just has an endpoint for getting a list of users from the database. And a users model, which just has functions for pulling data from the users table. Remember, a model is essentially just a collection of functions that are specifically used to interact with your database. So then your router doesn't have to interact with the database directly. It goes through the model. Okay, so let's start this up, start the server with npm run server. It's running on port 5000. Close those up. And open up Insomnia. or whatever you're using to make your HTTP requests. So let's just make 4 requests to each one of the endpoints that we have already, or just if you just want to do the first 2, just to make sure it's working. So we have a welcome endpoint, which is just the root route, just return a welcome to our API message. Good, that one works. And a get users route, which is just /users, get request, as return a list of the users in your database, which if you're just starting from scratch should be empty. So it's just an empty array. Now let's create a register route. So if you want to duplicate that or create one from scratch, we're going to make a post request to port 5000 /auth/register. And we're going to send through a username and a password as JSON as the request body. Okay, so I'll give you a couple minutes to get that set up. Okay, once you have that register route, let's make that post request, send through a username and a password, submit it, and you should see the object that was created for you. We've got an ID of 1 and your username. You should get a 201 created status. So let's jump into our database and see what it saved. So if you open up the database /auth.db file, just open that up in DB browser. And take a look at the users table. You should see the new user that was created with your username and your password. But problem, we're storing our passwords in plain text. Okay, this should set off all kinds of alarm bells. No good. Okay, so let's install bcrypt and start hashing these passwords. So we're not storing them in plain text. So first things first, let's just install bcrypt, the library. So you can say npm install, and it's called bcrypt.js is the library name. Since bcrypt is a hashing algorithm that can be used in any language, it's more of a spec, right? It's an algorithm. There's implementations in pretty much all languages. So bcrypt.js is the JavaScript implementation. There's implementations for Python or Go or Ruby or any other language that you're using. You can still use bcrypt in those languages as well. So let's install bcrypt.js. And restart your server. All right, first thing, let's jump into the user's model. This is where we're gonna actually hash the password. Because you see we have this add function that's actually inserting our data into the database. This would be a good place to just hash every password as it comes through, right? Then we don't have to put it in the router. So at the very top, let's import bcrypt. So we can say const bcrypt require bcrypt.js. Make sure you say bcrypt.js as a single word. It's not bcrypt.js because we're not importing a file, we're importing a library. So it's just one word, bcrypt.js. And then in the add function, let's hash our passwords before they get saved to the database. So we can just say reassign to the value of user.password. We'll say user.password equals, and we can say await bcrypt.hash. Very simple function that bcrypt gives us that will automatically hash our passwords securely for us. So we're going to say bcrypt hash. We're going to send through our password of user.password. And then the second parameter is the time complexity. So we're going to specify a time complexity of, let's just say 10 for now. And that's it. Now, anytime a user gets inserted into our database, before it actually gets inserted, we're going to hash the password and replace the value of the password with the hash. So go ahead and save that and try to recreate your users or your user. So now if we go into Insomnia, it's actually not going to let you create a new user with the same username. So just tweak your username before you try and create a new one. Add a 1 to it or something. Try and submit that. And we got a new user with an ID of 2. Let's see what that looks like in the database. So go refresh the database and look at that. We now have a new user, but this time instead of a plain text password, we have this long, crazy looking string. This is the result of the bcrypt hash. Okay, this is a hashed password. It's exactly what we want. Okay, you'll notice that it didn't take that long to make the request, right? It only took, in our case, in my case, it took 183 milliseconds, which is not that long when it comes to brute forcing, right? So let's try and increase our time complexity a little bit. Maybe instead of 10, we can use 16. Let's try bumping it up to 16. Save that and try and create a new user. See what happens. Change your username, let's say 2 this time. All right, there we go. That's taking some time. A little too long. All right, that one took 6.27 seconds on my machine, so a long time. It's probably a little too long, right, for a user to wait for that to create an account. So maybe 16 is a little high for our time complexity. If you look at the bcrypt documentation, you'll see that that number we pass is actually not the number of rounds. Okay, we're not saying hash the password 16 times. It's the time complexity, okay, not the number of hash rounds. So bcrypt is actually based on something called the blowfish cipher, which essentially means the number that we pass as the time complexity, this number right here. The number of actual rounds that it's going to hash is going to be 2 to the power of whatever number we specify. That's saying the rounds is 2 to the power of 16, coming from the blowfish cipher. So in that case, this is actually hashing it 2 to the power of 16, which is 65,000 times. So that might be a little high in our case, right? If we specify 10, we said 2 to the power of 10, if we specified our time complexity as 10, then that's going to be, it's only going to be 1,000 rounds, right? So that might be a little bit too low. So you really just have to find the sweet spot for your computer, right? Try and find the sweet spot for your computer so that the request takes about 1 second, 1 to 2 seconds to complete. So if you were doing this in production, if you were actually like deploying this application to a live server, you'd probably want to change your time complexity to make it 1 to 2 seconds on that machine, right? Maybe that machine's faster than your local machine. So you just kind of have to tweak this time complexity until it sits somewhere around 1 to 2 seconds. In my case, I put it at 14. Okay, 14 is the sweet number for my computer, which hashes it about 16,000 times. So if I set mine at 14, restart the server, try and create a new account, and it took 1.63 seconds. Perfect. Yeah, if you're on a slower computer, maybe you use 13 or maybe 12. So you'll see bcrypt, it gives us a lot of stuff out of the box. We don't have to specify, like, we don't have to write a function that hashes hashes. We don't have to write that time complexity from scratch. We don't have to write the hashing algorithm from scratch. It just kind of does it all for us. And the bcrypt hash that gets generated, it's actually kind of interesting if you look at it, because it includes the number of hashes in the hash itself. It includes the number of rounds or the time complexity. I actually think I have an image that I've used in previous lectures. Let me see if I can find it. Here it is. So this is essentially the bcrypt hash that gets generated. So you can see in this case that it uses the algorithm of 2A, which is saying that this is using the bcrypt algorithm. It has a time complexity of 10, and the resulting hash is a combination of the randomly generated salt and the hash itself. So in this case, when we're actually trying to validate a password, when we're trying to rehash a password to compare it to the one that we have in the database, we can see that we already know the time complexity, we know the algorithm, so we can essentially reproduce the same result. Yeah, Dennis, and if some hacker gets this hash and they look at it and they say, whoa, they set the time complexity at 1,000. Like, there's no chance that we're gonna try and crack this, and then they'll move on. Right? Hackers go for the low-hanging fruit. So the hash that actually gets generated, it's dependent on the algorithm. So this is the bcrypt hash. If you remember our examples, that's the MD5 hash. It looks a little bit different. Right? If you do a SHA-1 hash, it looks a little bit different. I think if I do this in here. Yeah, so a SHA-1 hash, it's a little bit longer. Right? Maybe a SHA-256 hash is a little bit longer. So depending on the algorithm, the hash is going to look a little bit different. Okay. So Vlad, why are we hashing in user's model, but not in the router, in post auth router? So we're just doing this for now. We're just hashing right in the user's model. So when a user is created, we can just hash it directly in the model instead of worrying about the router. Because if we reuse that function somewhere, let's say we have another endpoint that calls usersmodels.add, we wouldn't want to rewrite our hashing stuff, our hashing code, right? But in this case, since we have it in the model, we don't have to repeat it if we ever want to call that function again. Another question, so when this is hashed, is the time constraint dependent on the machine of the user or the server the website is hosted on? It's dependent on the server that the website is hosted on, okay, the computer that's actually generating the hash. So you would tweak your time complexity to slow down the code on the actual web server if you're on a live website. If you're just developing locally, then you would maybe tweak it to match your local computer, right? You're tweaking it to whatever computer is generating those hashes, whatever web server is running, whatever computer your web server is running on. Good question. Leslie, yeah, I actually see that error a lot. If you get that error in DB browser, database is locked, or if you get that in Node, that means your DB browser is probably locking that file. So you just have to go into DB browser and either click on write changes or revert changes. If you try and make some change in DB browser and then Node tries to make a change, it won't let you because DB browser locks that file to prevent changes from outside sources. So you just have to write the changes or revert them if you change anything in here. For anyone else that sees that, I'm sure someone else will come across that. So. All right. So we have our hashing happening in the register endpoint when a user is created. But what about logging in? Okay, right now we're not validating the password at all. If you look at the auth router, when someone logs in, all we're doing is we're checking to make sure that a row exists with that username, and then we're just assuming they're validated. We're not actually validating their password at all. So let's change that. Let's go into the auth router. We're going to go into the login auth route. And let's try to validate that password. So if we just follow the same code that we had before, this bcrypt code of bcrypt hash, let's try that. Let's say, let's import bcrypt in our auth router. And then once we get the user, let's try hashing the password that got sent to us in the request body. So let's say const password check, since password is already used. And let's say await bcrypt.hash password and give it the same time complexity that you used before. And then in your if statement, now you can just say if the user exists and if the password check is the same as the user password. And that should work, right? Since hashes always generate the same output with the same input. If you save that and you try it, it's not actually going to work. Let's try it. Let's try going into our Insomnia, create a request for login, make a request to a post request to auth/login, and send your username and a password as JSON body. So that's what we signed up with, right? JSON Maurer and ABC123. That's what we signed up with, so it should be correct. But if you try and submit it, it's not going to let you through. So when we're using bcrypt, we can't actually just compare the hashes directly. And there's a reason for this. Does anybody know why? Why can't we just compare bcrypt hashes one-to-one? Knowing how bcrypt works under the hood. Okay, one way, well, that really shouldn't matter, right? Because when we hash a password when the user signs up, and we hash a password when they log in, the hashes should be the same, right? So even when we compare the two hashes, they should still be the same. Yes, because it's salted, remember? The bcrypt algorithm automatically generates a random salt and it appends it to the password before it gets hashed. Remember with that random salt? So you'll notice when we signed up, when we registered, every single one of our accounts that got hashed, we used the same password, right? We used ABC123. But if you look in the database, every one of those hashes are different. Well, I guess, yeah, in this case, because we use different time complexities. Let's create a couple more with the same time complexity of 14. So if we create a JSON Maurer 4 with the same password and a JSON Maurer 5 with the same password, now go look at them in your database. You'll see that the hashes, even though they have the same time complexity, they're different, right? Because bcrypt is salting it under the hood. It's salting that password before it gets hashed. So it's not enough to just hash and compare in our login function. Luckily, bcrypt comes with a function that we can call that validates the hash to the password automatically. So under the hood, bcrypt is essentially going to say, all right, we're going to look at this hash. We're going to see it had a time complexity of 14. It used this algorithm. And then it knows kind of magically how to separate the password from the salt. And it's able to validate the password compared to the actual hash that's in the database. So if we want to do that, instead of actually hashing the password and just comparing it manually, we can now say, let's rename this to password valid. And instead of saying bcrypt hash, we can now say bcrypt compare. And we can compare the password from the request body. And we don't have to specify the time complexity because it already knows what it is from the hash, right? That time complexity is stored in the hash itself. So we just have to pass the plain text password and the hashed password, which is just user password. And if you look in the documentation for bcrypt, you'll see that that compare function, it returns a Boolean. It's going to return either true or false as to whether that password is valid or not. So now password valid, if the password is correct, then that value is going to be true. If it's not, that value is going to be false. So now instead of saying an equality check, we can just check directly for password valid. So if the user exists and their password is valid, then they are authenticated. If not, then they had invalid credentials. Let's try it. Save it. Let's jump into Insomnia. Try to make that login request again. And we have invalid credentials. Make sure you restart your server, save your files. Make sure I don't have any typos. Oh, that's why. Because we, on our first entry, when we first created our user, we didn't hash the password. I'm going to clear out my database just so I can start fresh. I'm going to clear out all these, delete those records, write my changes by clicking write changes. I'm going to just start fresh by creating a new user. So register a new user, Jason Maurer, ABC123. Okay, so now we have a new user with a hashed password and try to log in. There we go. Welcome, Jason Maurer. So now we're authenticated. Try to send that request with a invalid password. Maybe we just say ABC. And we get invalid credentials because that hash doesn't match what we have in the database. So now we're performing some very basic authentication. All right, how's everyone feeling so far? Make sure you update your poll in Slido. Feeling salty? All right, let's take another break, 5 minutes. Use the time to catch up or step away. I'll see you in 5. Okay, come on back. Are we good to move on, or need a few more minutes to rest your brain? Ken, you keep saying cannot get auth/login because it's a post request for login. Okay, it's not a get request, it's a post request. So make sure you do post login or post auth/login. All right, good to go, cool. You guys are pretty quiet during this lecture. I don't know how everyone's feeling. I hope everyone's feeling okay. We have tons of spare time. We're actually almost done with the content, so we have about 40 minutes. If anyone has any questions, if you want me to go over anything specific, feel free to ask in Slido. Okay, someone asked, is there a major difference between using the sync functionality, like hash sync and compare sync, versus doing it asynchronously? In this case, no, it's just syntactic sugar, really. If you look at the documentation for bcrypt, you'll see that there are methods for synchronous generating of hashes and asynchronous generating of hashes. Right? Synchronous just does it all in line. It doesn't use promises or anything. It holds the callback loop. It blocks any other code after that from running. And asynchronous works just as you would expect it with callbacks or promises. It's actually kind of interesting in this case because behind the scenes, the crypto functions in Node are all synchronous. Okay, when Node is running some kind of a crypto operation like hashing, it's going to be synchronous, even if the function is defining it as asynchronous. So in this case, there's actually no difference between using synchronous functions and asynchronous functions, just depending on what you want the syntax to look like. If you want to maybe be sure, like maybe in the future they release something that makes it asynchronous and you're already using the asynchronous functions, then great. Otherwise, you might have to switch over. But for now, to my knowledge, I don't think there's much difference between the two because crypto operations in Node are synchronous always. How do you clear out your SQLite or the revert, not highlighted so they're not an option? How do you delete the first unencrypted user? Just jump into DB browser, and if you just highlight a row, or you can highlight multiple rows by holding down Shift, just like you would in any other program. Just hold down Shift and select another one, and it'll select all the ones in between. And then you just hit delete record, the button delete record. And then once you do that, make sure you click write changes up here at the top, and that's going to write all of your changes to the database file and release the lock so that Node can work with it. Okay. All right, so challenge. Let's take 10 minutes on your own let's create a middleware function. We haven't written a middleware function for a while. Let's create a middleware function that restricts the user's endpoint. So this endpoint that gets a list of users, let's create a middleware function that authorizes a user based on the username and password passed as a header. Okay, so we already created this kind of template for a middleware function for you using async await, but just use this middleware function to authorize a user before they can access that endpoint. Let me put that in Slack. It's a good emoji for challenge. Okay, so challenge, create a middleware function that restricts the get API/users route to authorized users only. They should get the username and password from the request headers. Okay, so take 10 minutes, see if you can extract the code from our login endpoint, that bcrypt compare, see if you can extract that into its own middleware function so that we can reuse it. 10 minutes. Oh, I brought that down too low. There we go. All right, does everybody understand what we're doing? 10 minutes to see if you can get that to work on your own, and then we'll go through it. Don't post your answer in Slack if you're able to figure it out. Just keep it to yourself, and then we'll go through it. Yeah, you can't just sit and listen to the lecture anymore. You actually have to do something. Yeah, get the solution and then hash it and then post that in Slack. There'd be too many differences between like syntax and indentation and stuff. That wouldn't work. Maybe on Thursday when Don posts the lecture link, he'll hash it and you'll have to brute force the hash using a rainbow table to get into the lecture. That's a good idea. Take note of that one, Don.
I will give y'all a 2-day head start.
2 days to generate a rainbow table of like 100 million different hashes. See if you can brute force it. Sure. Does that work for you? Mm-hmm. Do you still need this file, Stephen, or can I switch it to the router? Cool. All right, 5 more minutes. When you're done, go ahead and click the I'm done button in the poly poll in Slack. Ray, Vlad, Daniel, nice. Everyone else, keep working, and we'll go through it. If you're finished, maybe take the extra time to add some additional checks, like maybe add an if statement to see if the user exists first before you hash the password. Make sure that the data that's getting passed through the headers is actually there. Should really be validating for 3 different things in this middleware function. Should be validating the password itself, the hash, right? Should be validating the user result from the database, and you should be validating the header values. All right, go ahead and start to finish up. We've got 5 people that got it done. Anybody else close? Give you a couple more seconds to finish that up. All right, let's just go ahead and finish it up. So first thing we're going to need to do is we need to get the values from the headers, right? So let's get the username and password from the request headers just by destructuring request headers. All right, cool. We've got the username and password. Let's validate that. Let's make sure that the username and password actually exist before we do anything. So let's say if the username is null or undefined, or if the password is null or undefined or falsy, then let's return an error. So we'll say return a response of a status 401.json, and then we can pass a message that says invalid credentials, whatever you want to say. Cool. All right, so we've got our data from the user. We're pulling it in through those headers. What's the next thing we need to do? We need to pull the user out of the database, right? We need to look up the user by their username. Same thing that was happening in the auth router, okay? The same thing that's happening here. So we can even just copy that line. Copy that line when we're looking up the user from the database. So we're gonna say const user equals await users model dot find by. We're gonna find by the username and just get the first result. Okay, maybe we can have another check before we actually even get on to hashing the password. We can say if the user doesn't exist, if nothing came back from the database, then obviously the user is not valid. So return that same error. Okay, this is getting a little bit verbose, right? Because we're repeating this same error message multiple times. So we could extract that and put it into a variable just up here and just say const auth error equals object that has the message in it, right? That invalid credentials message. And then everywhere we need to call that message, we just return that message, just replace that with auth error. Cleans it up a little bit. Okay, what's the last thing we need to do? So we've validated that the data came through. We validated that the user actually exists in the database. Last thing we need to do is validate that the password is correct, right? We need to validate the hash. So let's do the same thing we did in the auth router when we called bcrypt compare. Just copy that line. We're going to say password valid equals await bcrypt.compare, and we're going to pass through the password from the header, which is the plain text string, and we're going to compare it against the password in the database, which is user.password. That's the hashed version. Right, so we're comparing a plain string against a hash, and bcrypt is going to tell us if it's valid or not. So now let's run another if statement. We can say if the password is not valid. Okay, that's kind of different than what we were doing before. Before we were saying if the password is valid, then do something. But now we're going to say if it's not valid, return that same error that we've been returning before, the 401. So return a status of 401 with our auth error. Cool. So now if we reach this point in the code, once we reach this point in the code, we know that the user is now authenticated, right? We validated that the data is correct. We validated that the user exists, and we validated that the password is correct. So what do we need to do in this middleware function to move on? We call next, right? So now we can just call next, and boom, that middleware function is done. We now have a middleware function that can validate a user, and we can reuse it in any single route, or in any number of routes, I should say. Okay, so if we want to use it on that user's endpoint, when we're getting a list of the users, all we have to do is just come in here, and before our route handler, we just have to say call restricted. And there we go. Now the user, and no one, not just anybody, can request that endpoint. You actually have to pass a correct username and password to access this endpoint. Cool. This is just one way to do it. And those of you that came to solutions on your own, it might look a little bit different, but as long as it works the same, right? As long as it validates these three things and calls next, then you're good. All right, let's test it. Jump into Insomnia and try to make a request to get users just as it is without any headers. You get a 500 error. That's interesting. Oh, we have to import bcrypt, obviously. Don't forget to import bcrypt. Let's try that again. So server restarted, make the request from Insomnia. And actually I already had the headers. Forgot to delete those. Okay, so we don't have any headers, and we make the request. We get a 401 unauthorized, invalid credentials. Nice. That's what we should get if we just make the request without any headers. But now if we send username and password as headers, it's going to let us through because it's going to validate that these are correct. Boom, let us through. We got a 200 okay. What if we send a username that doesn't exist? It's not going to work. Invalid credentials, right? What if we send a correct username, but the password is incorrect? And we get invalid credentials. Cool. So now we have an authenticated, protected endpoint. Any questions about that? So Stephen asked, would you want to hide your restricted middleware, specifically the rounds of hashing, in an environment variable? What do you think? Do you think it's important to hide, maybe when we're hashing our password, do you think it's important to hide that number, to hide our time complexity? Is that sensitive information? Okay, no. That number, that time complexity number, that's not sensitive at all. That's actually stored just directly in the hash itself. Right, you can see right here between those two $signs, we have a time complexity of 14. So that's not sensitive information at all. The security doesn't come from hiding the time complexity. The security comes from the actual time that it takes to produce a result with the time complexity. Okay. So the number's not sensitive at all. Sarah, why do we call next twice? So we call next right here in the try if there's no errors, right? Just calling next without any parameters, it's going to move on to the next piece of middleware. But if we call next with a parameter, if we call it with an error parameter, it's going to bump it down to the error handler, which is an index. It's going to bump it down to this route handler right here if we call next with an error. So we have one next inside of our try if everything goes according to plan, but if an error gets thrown and we get bumped down to the catch statement, we're going to call next with the error. Yeah, I mean, if someone saw that you used 2 as your time complexity, that might be a little bit more incentive to try and create a rainbow table. But most of the time, even if your time complexity isn't very high and you're trying to hide the number, it would be pretty easy to find that out. Just put console.log, please don't hack, and they'll stop. That is the answer, Danny. You've just solved internet security. As long as you say please. All right, any other questions about this code that we just wrote? Is that crystal clear? It's pretty straightforward, right? We're just writing some validations and some if statements and returning errors if they don't validate. Cool. Now we can protect any endpoint, right? If we want to protect users, we just stick that in there. Let's say we had another one that was listing out a specific user by ID. We can just reuse the restricted function and just revalidate that way. We still have a little bit of a problem. If you noticed that anytime you make a request to a protected endpoint now, it's going to take quite a bit of time, right? It's going to take at least 1.5 seconds or however long your time complexity was. And that's because every time someone comes to our protected endpoint, we're rehashing their password, right? We're doing that over and over and over again. That's obviously still a problem. We don't want every single protected endpoint to rehash the password and take a couple seconds, okay? That's actually what we're gonna talk about on Thursday. We're gonna talk about how to fix that and how to use something called sessions to prevent having to rehash that password over and over again. But until then, just be content with the fact that all of your protected endpoints might take a few seconds. Yep, JWTs also solve the same problem. We're going to talk about that actually, we're not going to talk about that. I should have mentioned this before. We're actually, so your schedule next week, since it's a holiday on Monday, we're not going to have class on Monday, no lecture. And you're going to be given a pre-recorded lecture to watch in your own time on Tuesday. Okay, and then we're going to have a Q&A for like 30 or 40 minutes at the start of class on Tuesday regarding that lecture. So it's the topic is JWTs, the lecture that you're going to watch a video on, which is actually pretty simple. There's nothing too complicated to it. So hopefully it won't be too bad to just watch a video and have a Q&A session. So if you want to read up more on best practices for authentication, there was a link in the training kit, which is actually really cool, really helpful. It's a link on Google, just an article on Google about the 12 practices for user accounts. I definitely recommend you look over that if you get some time. It covers some things that we talked about tonight, right? It covers hashing passwords and protecting against brute forcing, complex password, acquiring complex passwords, things like that. Read through this in your own time and just kind of get a feel for some other things that go into authentication and making secure auth systems. All right, and that is it for tonight. Good luck with the project. This is actually a 2-day project, so only worry about part 1, and then part 2 is going to be on Thursday. So good luck with it. Have fun. And I'll see you guys on Thursday.